All right. Hello and good evening, everyone. My name is Brian Fitzgerald, and I'm the Director of Science and Education, Director of Education currently at Mount Washington Observatory. Thanks so much for joining us for tonight's program. For those of you who aren't already familiar, Mount Washington Observatory is a nonprofit, member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. The way that we accomplish that is through operating our Summit weather station with around-the-clock weather observation and forecasting, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions for tonight's speakers and you're joining us via Zoom, please use the Q&A button. You can find that at the bottom of your screen there. And we'll make sure to get as many questions in for our speakers this evening. And speaking of our speakers for this evening, we have both Dr. Lourdes Aviles from Plymouth State University, who's a professor of meteorology there, and Mount Washington Observatory staff meteorologist Ryan Knapp, who will both be sharing their knowledge all about auroras and atmospheric optics. So once again, if you have questions for either of our speakers this evening, make sure you use the Q&A button if you are joining us through Zoom. If you're joining us through the live stream on Facebook, welcome. Thanks for joining us there. Feel free to leave questions for us. We won't be able to get to them live during the program, but certainly we'll follow up afterwards and respond to as many questions as we can. If you'd like to join us for an upcoming Science and Mountains program through Zoom, make sure you register over at mountwashington.org/SITM. Alrighty, well, before we kick things off this evening, we have a poll like we usually do for our audience on Zoom. I'll go ahead and launch that series of questions. We have 5 questions for those of you joining on Zoom tonight. First off, we're curious where you're joining from. As always, we have a number of states listed here. Perhaps you're joining from within New England, perhaps outside of New England, or perhaps even outside the US of A. Love to know where you're joining from for this program today. Secondly, we're curious, have you joined an Observatory Science in the Mountains program before? Maybe it's your first program, maybe you've been here before, maybe you've been here a lot, you've been attending most of the programs. We'd love to learn more about our audience and hopefully a little bit about what keeps you coming back as well. So thanks for joining. And then we have 3 trivia questions from our speakers from this evening that we'll get those answers covered for you at some point tonight in the presentations themselves. But some good trivia, the first one being, in what year did the strongest aurora event on record occur? Was it in 1776, 1859, 1989, or more recently in 2003? Next, what color does not ruin your night vision? Is it red, yellow, green, or blue? And then finally, how often is Mount Washington in the clouds or the fog, thus making aurora not possible? 10%, 30%, 60, or 90% of the time? Get your answers in there. I see most of you have participated already. We'll give you another 5 seconds or so to get your answers in. And we'll close it out in 3, 2, 1. Alrighty, we'll go and end the poll there and share some results with everyone. So if you're on Zoom, you should be able to see some of those results in front of you. Neck and neck, New Hampshire and those joining outside of New England are the winners there for the most numerous visitors to our program tonight. But we have representation all across the region here, including outside the country as well. 4 of you joining from outside the country. Thanks so much for joining the program. Curious about if you've joined a Science and Mountains program before? 40% of you are a first timer. Welcome. We hope to host you again for an upcoming program and that you'll join us for another exciting program next month as well. And for those of you who have joined before, including those of you who have been here for most of the programs, 23% of you, thanks so much for continuing to show interest in the program, and hopefully we're delivering for you. All right, and then on to the trivia. What year did the strongest aurora event on record occur? 1989 was, well, that was the most popular answer there, flanked by 1859 and a little bit by 2003. Most of you, 63% of you, thought red is the color that does not ruin your night vision. And then most of you thought Mount Washington is in the clouds 60% of the time. Some of you thinking perhaps 30%, some 90%. Alrighty, so great, some fascinating answers there. Thank you for participating in that poll. And without further ado, I'd love to welcome our speakers, both Lourdes and Ryan. Can both of you see me? Can you hear me? Hopefully you can.
I can hear you.
You will.
All right, well, that's great. Even better. I can see both of you and I can hear both of you as well. So by all means, take it away. We'd love to hear all you have to share tonight about aurora and atmospheric optics.
All right, so I'm going to get us started here. Let me share my screen. And one more thing to hide the controls. All right. So good evening, everybody, and thank you so much for being here. And also thank you for Brian for hosting the Science in the Mountains series. And tonight, oh, there you go. My name is Lourdes Aviles. As Brian said, I am a professor of meteorology at Plymouth State University. I'm the chair of the department. But also, I just became, just last year, a trustee of my Washington Observatory, and also relevant, I'm a trustee of the University Corporation for Atmospheric Research. The courses that I tend to teach are physics, atmospheric physics related, dynamic meteorology, and the research that I like to engage in is interdisciplinary connections of atmospheric phenomena with other sciences, with history, etc., especially history and science of phenomena. I am originally from Puerto Rico, but I lived here in New Hampshire for almost 20 years. And I've done other work, but I have been fascinated with the colors of the sky since I was a little girl. Some of you might know me from my work with the Great New England Hurricane of 1938. I published a book 10 years ago, and but I have been giving presentations throughout the state and throughout the region, more than 50 by my count. So you might have, some of you might have come to one of my presentations. I am joining you right now from Plymouth State University, from my office here, beautiful Plymouth State. Those pictures there show you the different views. This is a view from the science building. The one on the left is a picture. The one on the top right is our view from the weather center. And the bottom right is a webcam image. So I tend to have a lot of fun looking at our signature building, the Rounds Hall clock tower, from up here. Just a handful of weeks ago, on March 23, 2023, turns out that we had the strongest aurora event that we have had, the world has had in the last 6 years, and certainly the strongest here in town that was visible from here in town since 2004 or so. And our webcam, which turns into black and white at night, actually captured it. The one on the left is before anything started. And then the two on the right are two screenshots of the webcam as the aurora was very strong. I spent the time sleeping. I did not stay up. I did not realize what I was missing. But thankfully, one of our students went to the roof of the building and took this amazing picture that has been shared all over. So that made me feel a little better having this picture. But also, it's probably going to be a while before I have a chance to make up for my mistake and take this kind of picture myself. So the atmospheric optics that I work with, that I am writing and studying the science and their historical connections and the cultural connotations, the history of how we learned about them, all that. It's everything that you can see in the sky. And sometimes you need clouds, sometimes you need the clouds to get out of the way. It depends on the on the optical effects. Sometimes you need ice clouds, sometimes you need water droplets, sometimes you need rain. So it varies a lot, and it is a lot. I am currently working on a textbook on the science and history, an introductory textbook on atmospheric optics. And it will be published by the American Geophysical Union in a couple of years. It takes a while to work through one of these. So tonight, we will talk a little bit about the optics that you can see at Mount Washington, a brief overview, a little bit about the historical events, and I'll tell you the answer to the question in the trivia. A little bit about the science of auroras, different aspects of it. Then Ryan will take it to talk to us about photographing the aurora and finding them in order to be able to take those pictures. And then we'll wrap up with, you know, what would happen if there's a really, really strong event. So Mount Washington, famous for being the place with the worst weather in the world, right? And this video taken from the observation tower toward the tip-top house was all over the media. It looked like, you know, an alien planet. And this was the day when we had a wind chill almost minus 110 wind chill degrees Fahrenheit. And also tied the modern record of minus 47 degrees. So the optics are not going to happen at those times. But given that the mountain is covered in clouds and fog, here's one of the answers, 60% of the time. And for many of the optics, you do need clouds or fog. There are plenty of opportunities, if one knows to see them, to see optics on the mountain. So this is a fog bow that you can see sometimes when you have fog or a cloud and it's illuminated by the sun. Here are other pictures. So here's the thing. Tonight we're gonna cover mostly auroras, and maybe Brian will let me come back for a part 2, where I will talk about the science related to all of these effects, but I will at least tell you what they are. Here in the top left, we have light pillars, then a portion of a rainbow with some crepuscular rays, then a fog bow as looking into the summit. In the second row, we have what's called a glory, and also the shadow of the mountain. Then we have a couple of ice halos, a 22-degree halo and upper tangent and lower tangent arcs. We have some more crepuscular rays as seen from the mountain. Then in the bottom, a more regular rainbow. We have shadows of clouds, and we have a sun pillar. All these pictures were taken from the summit or looking at the summit. Of course, we have this image that Brian likes to use as his background for these programs, but that's obviously the observation tower, covered in rime, ice, but also with a magnificent aurora in the background. And because the mountain is covered 60% of the time in clouds, Mount Washington is not a great place to go to take your aurora pictures. But if you're stuck up there, like the observers are, and you're lucky to have a clear night, you might be treated some really spectacular views. And this is what I'm going to focus on more tonight, talking about the science of the aurora. And all these pictures I just showed you, the optics from the mountain and these aurora pictures were taken by Mount Washington's own photographer extraordinaire, Ryan Knapp, my collaborator tonight. Ryan, do you want to introduce yourself?
Sure, thank you. My name is Ryan Knapp. I'm originally from Northern California, and I got my BS in meteorology from San Jose State. That's located just south of San Francisco in California. Previous to working on the summit, I did a little bit of aviation meteorology as well as forensic meteorology, weather observation, and modeling and simulations, as well as some fire weather. But since late 2005, I started as an intern on the summit, and then in spring of 2006, I got hired as a full-time observer. So I just surpassed my 18th year up on the summit as the senior staff meteorologist up there. And as Lourdes has pointed out, I do take a lot of photos. So a lot of the photos that you're going to see from or of the summit are mostly my images. There are a few that are from outside, but the summit provides some great optics, as Lourdes kind of touched on. But I'll kick it back to you, and you can talk a little bit more about the Northern Lights that we get to see.
All right. And you don't know how happy it makes me that Ryan takes all these pictures. So here we go. Let's talk a little bit about the ancient times before we understood what we were looking at. And auroras, obviously, if they happened, they were very noticeable, especially with the very, very dark skies that you would have had before light pollution came into being. So in the northern latitudes where these events occur, the native people made them part of their mythology. In Alaska and in the Vikings and all that. So humans tried to explain the unexplainable. So they created stories of the auroras being bridges, a way for spirits to passage to the other world. Snakes, the one on the right there. Oh, my computer wants to update. Not a good time. And also, when you had very, very active events and they would make an appearance in the middle latitudes, that was not too often, sometimes people would give it significance, sometimes as bad omens, as harbingers of war, for example. So, but then eventually we started to understand them and study them scientifically. And it took a while because the science is very complicated and there's still questions we don't have answers. But we know a lot more now than 1,000 years ago when we were first trying to explain them. So here's your answer to the second trivia question. It was the 1859 Carrington event. It is the strongest on record as far as we can tell. So there were a couple of days in 1859, and I'll tell you more about it later, but the auroras were seen around the entire world, including all the way to the tropics. And the reports, there were a lot of newspaper reports. We obviously don't have any pictures because even though photography existed back then, it was not accessible. It was experimental and it would not have been good enough anyway to take pictures. So the reports said things like you were able to read the newspaper by the light of the aurora because they were so intense. Not only that, but what causes these auroras that I'll talk about more in a second have to do with a lot of electrons raining into the atmosphere. And sometimes electrical currents are induced on the surface. And back in 1859, the telegraph was a very modern way of communication. And the reports were that first of all, a lot of interference in telegraph communication, but also the power was fluctuating so much that they turned them off. They used batteries back then. But even though they turned them off, they were still being able to send messages with the telegraphs off because the currents that were being induced were so strong. So obviously, we didn't have measurements of the strength directly, but all this suggests that this was and still is the strongest event. Some of the ones we put in the trivia were also very strong. The one in 1989 left the city of Montreal without power. And in 2003, there was a solar event that created a really, really strong aurora. So those were legitimate strong aurora events, but none as strong as this 1859 event. The one on the right, I came across more recently, and it was in 1770. And the reports are that for 9 days in a row, there were red auroras seen all around the world. And these were, the red auroras mean that the mechanisms were a little different, and I'll talk to you about the colors in a little bit. But these were found in drawings in Chinese diaries. Plus, there were some reports. Captain Cook, the British explorer that did a lot of Southern Hemisphere and Pacific Ocean exploring, also noted them in his logs. So here's a couple of pictures of those Chinese diaries that were found with pictures of what people interpreted they were seeing. And they were definitely red auroras. So I've been talking about auroras all the time. The aurora is what we sometimes refer to, and probably more commonly referred to, as the northern lights. So in the northern hemisphere, the northern lights are the Aurora Borealis, and in the southern hemisphere, the southern lights are the Aurora Australis. So aurora means dawn in well, it originates with the Roman goddess of dawn. Her name was Aurora. Borealis comes from the wind of the north, the god of the north wind, which was a Greek god. So we're mixing Roman and Greek mythology. And Australis means southern in Latin. So these things were named at different times, and that's why we kind of mix them up. The first person to name them was none other than Galileo Galilei. He wrote an essay in Italian in 1619, where he spoke of the lights as looking like dawn was coming, but from the wrong direction, from the north. If you're in the middle latitudes, the aurora is gonna most often show up to the north. So he called it the dawn of the north. And that's where Aurora Borealis, the name, came from. So they happen in an oval. So there's a misconception that people have that auroras only happen when there's a strong solar event. And this is not correct. The auroras are happening constantly. They're just not near anywhere near enough, near to us. So they take on the shape of an oval because they are longer or further out away from the sun. So they're always strongest exactly away from the sun. So that's why local midnight is when they normally happen the strongest, when you can see them. And they are centered not on the North Pole and the South Pole, but on the magnetic pole, which is a little shifted near Canada right now, although they can move. So these ovals are where the aurora happens all the time. And when the solar activity causes an enhancement of it, that's when we might be able to see them from here. So let me show you this animation. This is the same model. This is the model that just shows where auroras are. This is the line that separates daytime and nighttime. And you can see the oval. There's a little bit on the daytime side, but most of it is in the nighttime side. And it moves around the world with nighttime. And if we're ever going to see them from here, it's going to be near on either side of midnight. This one was not really strong enough for us to see. So auroras are always happening, just not near us. So here is, I got this from a publication from a textbook that shows this oval. 0 is local midnight, 12 is noon. So they're always kind of elongated toward local midnight. And, you know, when activity is moderate or active, then it moves to more southern latitudes. And again, this is respect to the magnetic pole, not the geographic pole. So because there's a shift back and forth depending on solar activity, there's a region around the world where auroras tend to be observed more often. So that's like a statistical probability area that is called the auroral zone. So the oval is day to day, whatever you're seeing, whatever's happening. And the auroral zone is the area around the world where you are more likely to see the lights. And I found this nice visual that shows this red with the 100 is where you're the most likely to see them based on statistics. And you can see that northern Canada, and then here, the southern part of Greenland, Iceland, the Scandinavian Peninsula, northern Russia, and Alaska. Those are the places that tend to be under the auroras more often than other parts. And you can see if you look toward the bottom, the northern part of the US has a 5. So you can think of it as a percent in comparison. So there's only 5% of the time would you be able to see the auroras down here. And most of the time they're not over your head, they're to the north, but because they're very high in the skies, I'm going to show you in a second, you can see them from far away. So how high? Very, very, very high. This image on the left here is the height where auroras were observed for thousands of aurora events. And you can see that most of them, this would be the bottom of them, or, you know, the height observations they did, are around 100 kilometers. And all the way up to about 500. And I'll show you what that means in a second, but this picture was taken from the International Space Station, which is just above where the aurora is. So the space station on average flies at 400 kilometers, which is still within the Earth's atmosphere, but definitely way up there, orbiting rather than flying. So you can see the green auroras and you can see a little reddish on top. So where is that? It's all the way up here, 100 kilometers. So if you remember your middle school science, the atmosphere has the layers, the troposphere, the stratosphere, the mesosphere, the thermosphere. All the weather happens down here in the troposphere. This is also where Mount Everest, I imagine this triangle here is Mount, oh yeah, right there, Mount Everest. So we don't make it past the tropopause. This is also around where airplanes fly. So everything happens down here. Then in the stratosphere, you have the ozone layer. In the mesosphere is where most of the meteors burn. So all the way up here at 100 kilometers within the thermosphere is where the bottom part of the auroras are. And they can go way higher than that. So let's talk about the science. The first thing you need to know is that these ovals of auroras that we see, by the way, these are not actual pictures or satellite images. These are a model forecast that I just grabbed a screenshot of a couple of weeks ago. So the auroras, as spectacular and magnificent and fascinating as they are just a tiny, tiny little visual sign of the interactions, the really, really vast interactions between the sun and the earth. So that they're just a little visual sign of science that is way, way, way more complicated than than even I have learned about, and certainly than we are going to cover tonight. But I'm going to give you enough to get a taste of it. So it all starts with the sun. The sun is, of course, that star in the center of our system, and all the planets, not to scale, orbit around the sun. And the sun is really a gigantic ball of plasma that is engaged in thermonuclear fusion, turning hydrogen into helium, and that produces a lot of energy. And all the sunlight we get and everything that we get from the sun is because of what's happening in there. It's really, really violent processes. And because of everything that's happening in the sun, there's a lot happening in the sun that we don't have the space here to go into, but we are constantly receiving particles from the sun. There's particles coming out of the sun in all directions. This is called the solar wind. And these particles are very hot and very fast. They move at nearly 1,000 miles an hour, 400 to 500 kilometers per second or meters per second. And they're electrons, and they are molecules that have lost their electrons, so they're positively charged. And in fact, those materials coming out of the sun reach way outside of what we think of as the solar system, all the planets and everything, and it's called the heliosphere. So you can think of the heliosphere as an extension of the atmosphere of the sun. So in a way, we live in the atmosphere, inside the atmosphere of the sun. So this is not a linear scale. The one astronomical unit is defined as the distance between the Earth and the sun. So that's 1. And then 10, you make it all the way to Saturn. And 100, you're almost to the end of the heliosphere. And 1,000, you're way outside. So the influence of the sun goes all the way to about 100 astronomical units, way, way, way outside, 100 times outside of where the Earth is. So you have the sun, you have the solar wind coming, and with it comes a magnetic field that covers the entire heliosphere. And the Earth is sitting there. If I show you that image I showed earlier, you might or might not have noticed this little ball here, which is the Earth. So the solar wind, the Earth is nothing like, it's like a pebble to this solar wind and the magnetic field coming from the sun. But to the Earth, the interactions with the solar wind and with the magnetic field from the sun are huge. Now, you might have learned in middle school science that the Earth has a magnetic field. So what we have is that the core of the Earth, part of it, is liquid, and it's really hot. So you have, iron and other substances there that have lost the electrons, and the atoms are just moving there in a soup. And electrical currents are formed because every time you have electrons moving, you have an electrical current. And when you have an electrical current that is moving in circles, you actually create a magnetic field in the shape of the bar magnetic field. And that's what we have for the Earth. And you might have learned that the Earth has that. But turns out that that's just if you're close enough. If you back off here on the bottom right, you see that the magnetic field of the Earth gets distorted because of the interaction with the solar magnetic field, that heliospheric magnetic field that comes with the solar wind. And I like to think of this as a sideways spider. So it looks like a spider. And that magnetic field of the sun wraps around the magnetic field of the earth and turns into this thing with a long tail. So the scientists speak of what they call a magnetic sheath, like the sheath of a sword. So the earth is sitting in there, protected from the solar wind and the solar magnetic field by its own magnetic field, which is very convenient. So, but not all the solar wind stays out. Some of it actually gets trapped in the magnetic field of the earth. So I did some screenshots of a video here. The top left shows in yellow the magnetic field that comes with the solar wind, and in blue the magnetic field of the earth. When they interact, sometimes, when they kind of, it's called reconnection, when they kind of snap together like a bubble, two bubbles together, some of the solar wind particles actually get transmitted toward the planet, but that is the daytime side. So we wouldn't see the auroras during the day, and they don't have as much energy. So instead, some of the magnetic field actually gets wrapped around the magnetic field of the earth, and then it connects again and snaps in, and then more particles come in, and these ones are accelerated, so they have a lot of energy, and they are on the night side. So those are the ones that give us the auroras. Now, it doesn't really matter for our purposes, but interestingly, these particles, which are mostly electrons, but there's protons as well, they don't come in a straight line toward the earth. They coil around like that cable, that the electrical cable around the magnet. They coil around the magnetic field lines as they come toward the earth. Sometimes they're trapped and go back and forth, but some of them actually are energetic enough to go into the atmosphere. So if we look at this somewhat complicated looking graph, you might remember also from middle school science that the atmosphere is about 20% oxygen and 80% nitrogen, but that's down here all the way to 100 kilometers. So most of the atmosphere, but the auroras, the bottom of them happen at 100 kilometers, and they can go all the way to about 500. So this is where the auroras happen. And at those altitudes, oxygen starts to dominate, and you still have a lot of nitrogen, but quickly diminishing. So the gas that those very energetic electrons come into contact with is oxygen. And that actually is important for which colors we see. So what happens is those very, very energetic electrons, they collide with the atmosphere, they break some of the molecules apart. That's why instead of O2, you get O's. Sometimes they rip their electrons off, or simply they also can increase their temperature by making them move faster. But what matters to us is that some of the atoms get excited. And if we look at an atom of oxygen in the old model of how atoms work, you have a nucleus, you have electrons around. This is not really how atoms look. It's more like this on the top left, and those bubbles are areas of probability where the electrons might be, but it's not as useful for our purposes. But anyway, so the oxygen gets excited. One or two of the electrons get pushed into a higher energy level, but nature does not like to be in a higher energy level than it needs to. So when those electrons can go back down to a lower energy level, they release the energy in the form of light. So for green, you're going from a higher excited state to a lower still excited state. For red is from a not as high excited state to a ground state. So atmospheric gases excited by electrons coming down. By the way, the scientists use the terminology of precipitation. These electrons precipitate, just like literally they're saying that electrons are raining into the atmosphere. Not all the electrons come directly from outer space, from the solar wind. Some of them are electrons that were already in the atmosphere but had been energized by interacting with the solar wind. And again, this is just a tiny little amount of all that solar wind that gets past us and that the magnetosphere protects us from. So this is how those electrons and other charged particles coming from the solar wind end up causing the auroras. And this is how the ovals, the auroral ovals, or the northern and the southern hemisphere exist. Now, when people say that you can only see auroras when you have solar events, it's not that they're wrong, it's that when those solar events happen is when we are more likely to be able to see them, because the auroras can be enhanced, and they can be enhanced to be more energetic, to have more motion, to have more intense light coming, more intense colors, and also more colors, and be seen in a wider band of latitudes, and also latitudes further south. So this image here on the bottom right has this index, this KP classification. Then when it's low, you know, the oval is pretty far north. And when the number is high, and we'll talk more about that, the oval is not just wider, but also reaches further south. So we'll talk more about that. But what I want to talk about is what types of events can cause that enhancement. And they originate in the sun. So a solar flare is a very sudden flash of light coming from the sun. We don't necessarily fully understand exactly how they happen, but they have to do with this very wild magnetic processes and plasma processes in the sun. The bottom right picture is an X-ray image of the sun. The sun doesn't normally emit a lot of X-rays, but during solar flares, it emits a lot. It is a flash that only lasts for a very short time, but is really blinding, especially in wavelengths that are not normally coming from the sun. So that's a solar flare, and that's light. And we see that in a few minutes, which is as long as it takes sunlight to reach us. We can also have what's called a coronal mass ejection. And those normally occur, but not, you know, they tend to be associated with the solar flares. And there's all sorts of other types of events that can make that solar wind more energetic. But the coronal mass ejection is actual solar particles coming off the sun, kind of in a bubble. And that can happen in any direction, but sometimes it's directed toward Earth. So when it's directed toward Earth, we get this huge amount of much more energetic solar wind, which means that the electrons that are coming in, those that sneak through the magnetic field, are a lot more energetic. There's more of them. You know, they can go deeper into the atmosphere. They can cover more latitudes. Now, the coronal mass ejections take, on average, about 3 days. If you have an especially strong one, it could be less than that. That Carrington event in 1852 occurred just after the first observation of a solar flare. At that time, people like to draw the sunspots a lot with solar telescopes. And suddenly it became really bright, and then it went away. So they didn't know what they were seeing, but it was the first observation of a solar flare. And it was a day and a half later that the first of the aurora sightings occurred. So that's a lot faster than normal. which also jives with the much stronger event. So this is an artistic depiction showing you could say it's a coronal mass ejection material from the sun. Oh, and let me go back for a second. The corona is the outer atmosphere of the sun, which is so hot that it emits radiation at wavelengths that we cannot see, except for a tiny little bit, and except for when the sun is blocked by a solar eclipse, or, you know, instruments like this one that block the sun. So lots of excitement. Next year, there will be a total solar eclipse that will be visible from the US, and also very close to us here in New Hampshire. So those pieces of the corona of the sun, if they arrive to Earth, they can cause much more energetic auroras that allow us to see things like the picture that my student took while I was sleeping. So those are the ones that if we can anticipate them, which Ryan will talk a little bit about those in a little bit, then we can at least know there's a better chance for auroras to be seen in the middle latitudes. So again, the whole science of these interactions and the solar processes and the Earth processes and how they occur, it goes way, way deeper than what I just described. But it's hopefully, you know, deep enough for those that are interested to understand, you know, the complexity and the depth of these really, really complicated phenomena. One of my favorite things to talk about is the colors of the aurora. So in order to talk about that, we need to remember that white light, the sunlight, is made of all the colors of the spectrum, and you can separate them with a prism. You might or might not know that we can assign a wavelength to each of those colors, with reds having the longer wavelengths and violets having the shorter wavelengths. So when we see green from the oxygen atom getting back to a lower energy state, we are seeing a very, very specific wavelength of light. And that wavelength corresponds to the energy difference between those two states. So there's an entire science of spectroscopy that is used to measure the emissions from different atoms, so you can actually use that to identify them. So the oxygen in the upper atmosphere has emission lines in the green and in the red. And I found this awesome interactive viewer that you can click on and off. It's not live, these are just screenshots. You can click on and off the different atoms in the upper atmosphere, and it tells you what colors it can give you for the aurora. So let's go over those. Most auroras are green, and that green is from oxygen. The oxygen that monoatomic, so just the 1 O, up there in the 100 kilometers or so. Even though there might be a little oxygen below that, the atoms lose their energy to collisions with other molecules. So you need to not have as many air molecules in order to be able to see this green. So then the red, if there's any red, is going to be above the green, is also coming from the oxygen, but it's even harder for the atoms to release that red light without losing it to other atoms, because they have to keep it for a very long time. So only above 200 kilometers or so is the air thin enough to not lose the energy and to have enough red emissions. So that photo from the space station with the faint red is usually a lot fainter than the green, because there's a lot less of it being emitted, and it's harder takes longer, it's further away. This image that Brian likes to use as his background also shows green below and red above. So this is about 100 kilometers to 200. This is above 200 kilometers. Now, once in a while, there's a lot of electrons that don't have as much energy to be able to do the green transition, but have enough energy to do the red transition. And there's so many of them that you end up with a red aurora. That is a lot rarer, but when it does happen, it can be very shocking. This is a picture from Spain, so it's not one of Ryan's images. But that one of the images I showed you before is a paint or a drawing from medieval times showing the red aurora in the background, and an omen of war, as they believed. Now, you might remember that there's still a lot of nitrogen, this blue nitrogen atoms, and nitrogen has a lot of emission lines, some of them in the blue, some of them in the red. The height of the lines is the intensity. So, but nitrogen is also a lot harder to excite. So you need very, very excited electrons coming in that can break through a little lower to 85 kilometers or so. So if you see pinkish or purplish colors below the aurora, that's from nitrogen. So that's below the green. Sometimes it looks pinkish, sometimes it looks purple, sometimes it looks more red. And it's because you can get either reds or blues from it. Sometimes it can also look yellow. There's no yellow emissions in the aurora, but the bottom emissions, if they are red mixed with green, you might have heard that when you mix green and red light, you get yellow. So if you see yellow in an aurora, it's because you're seeing the red from the nitrogen below, and it's a very strong event, and the green from the oxygen. Sometimes the nitrogen gets ionized, which means that its electrons are ripped off. That is also very hard to happen, and it needs very, very strong electrons. And if you see those, they are above the green. So if you see violet above the green, that's from ionized nitrogen, and that tends to be way higher, up to 300, 400 kilometers above. So this is one of my favorite photos from the observation deck of Mount Washington. And here's another one, not from Mount Washington, but also by Ryan, showing that the green is mostly covered by clouds below, but you can see the violet above. And I believe this was a lightning bug that kind of photobombed. Another interesting thing that can happen is that the sun, the UV light from the sun, which we cannot see, can excite the nitrogen, enhancing those violet emissions. So when you see an aurora where the green is kind of straight, but the violets are tilted, is because the sun from down here is illuminating the top of the atmosphere and enhancing the ionization and allowing the nitrogen to emit violet. So again, all these pictures were taken by Ryan. So I will now pass you to Ryan so he can talk about how to photograph the aurora.
Alrighty, well, thank you. So your best gear is the gear that you have available, and most people have a smartphone in their pocket, or might be even viewing this podcast tonight on it. And most modern smartphones can do night photography. Now, most cameras are kind of built nowadays for low light photography, but a lot of them are now allowing you to shoot things like the Milky Way as well as the Northern Lights. But there is some tricks that you kind of have to know and have available in your pocket. before you go out. So the first would be something to keep your camera steady. So a tripod would be ideal, but if you don't have a tripod, just lean your phone up against a rock or a piece of wood or something that's available around you that can kind of keep it still, because you don't want to handheld it or hand hold it, because you're going to be shaking it, and a lot of the image stabilization software is going to try and make up for that. So if you have something that can keep it steady, you'll have a nice clear shot. The next thing is to see if your camera has the ability to do a shutter delay. So some smartphone cameras can do a 2, a 5, or a 10-second delay. So you'll hit the shutter button, and then a giant countdown of 1, 2, 3, 4, or 5 will go onto your screen and kind of count down until it takes the picture. That way you can push the button, set it down on wherever you're trying to set it up to keep it steady, and then allow the picture to be taken. The next would be if your camera phone can take a RAW format if available, but do note that RAW photography takes a lot of file space. So if you're not really comfortable with that, it might be something that you maybe dabble in later down the road, and not so much when you're first starting out, because it can take a lot of memory. And if your phone doesn't have a lot of memory available, you're going to limit yourself on how many shots you can take. So, but that is something to kind of delve on later in life. You can do a whole lecture series on how to do raw editing and whatnot. And then the last thing is if your smartphone can do manual control. So if you can control things like ISO, exposure, or the f-stop of your camera, that would be ideal, because then you can make it, a longer exposure or more bright with the ISO or elements like that. But not a lot of smartphones allow that, but more and more developers are baking this into their software to allow the user to have full control of their camera settings. So if you can, that's great, but if not, it's not the end of the world. Next up would be DSLR mirrorless cameras. Those are more what you see of most people taking photos of them, because they have a larger sensor which can take in more light. But again, the fundamentals are almost the same. So again, you want something steady to put it on. So a tripod would be the best thing, or the easiest thing to put it on. A time shutter delay, but a lot of the cameras can even do intervalometers, which will allow you to do several images in a row. So that way you can maybe do a time lapse, or you can just kind of set it and not worry about all the settings from shot to shot, or a remote trigger. So that way you can kind of activate it remotely without even shaking the camera by pushing the button. Again, the RAW format would be your ideal setting, but if not, JPEG will get most of what you need done, especially if all you're intending to do is put it on social media or share with friends and family. Manual controls are almost ideal, but if not, aperture settings, aperture priority or shutter priority, those two can also work if your camera has them available. The wider your lens is, the better. The wider your lens is will allow you to do longer exposures, and we'll touch upon that in a second. And then the last one is hand warmers and rubber bands. You're going to attach those to your lens, because your lens is essentially a giant vacuum. And if you're going into the locations that I'm about to note, there's going to be a lot of condensation in the air, and the hand warmer will keep your lens from fogging over, because sometimes it'll be cooler or warmer than the outside air, and your lens will fog up, and you don't want to be rubbing the front of your camera and adjusting or moving it too much. So we'll talk about the settings if you do have them available either on your smartphone or on your camera. So the ISO is your main setting that you're going to be tinkering with. The higher you put your ISO setting, the brighter your image will be. But the downside of doing that is you're going to be introducing a lot more noise into your photography. So you're going to want to dial that down. So each camera has its own little sweet spot, and you're going to have to figure that out on your own. There is no ideal setting. But what I would do is start high and then work your way backwards and see which image has the sweet spot of noise for your camera. A lot of modern cameras can go way, way high on their ISO, whereas older cameras or smartphones, you're going to want to keep those in the lower range because you're going to start getting a lot of grain and noise and little dots in your images if you don't. Exposure times, smartphones, for the most part, kind of lock that in a walled garden. So there isn't a lot you can do, but some smartphones, again, allow you to dial that up to several minutes if you can. And then it does kind of software to kind of clean up the image and align all the images and everything else. But most kind of put a limit of 10 to 30 seconds, or they don't even allow you to touch that. If you have your camera, the amount of time that you're going to have available is either the 500 or 400 rule. 500 is if you're just planning to put it on social media. 400 is if you're planning to print the image, because you're going to have less of a star trailing effect. But essentially, you're going to take the number, either 500 or 400, and divide it by the width of the lens. So the example that I have here for 18 millimeters would be 500 divided by 18 would be roughly around 27 seconds, or if you used 400, it would have been about 22. Some cameras allow you to do up to those incremental seconds, but most you would probably have to limit yourself to just that 20-second or maybe 25. And then lastly is the aperture. So the wider that your aperture is, the smaller the number, essentially. It's kind of the opposite of what most people think, but the smaller that F number is, the wider your aperture is. So it'll be a wider lens. Aperture will allow more light in. So if you have an f8 or an f4, it's going to be smaller, whereas if you have an f2.8, it's going to be nice and big to allow more of that light hitting your sensor. So next up, we'll talk about some other notes. The best thing I can say is just practice, practice, practice. So you don't want to wait until a Northern Lights event to go out and learn how to do night photography. You're going to have to go out before the auroras occur and kind of learn what a typical night view looks like, because there's a lot of light pollution, as we'll talk about in a second. And also you want to learn how to use your camera and smartphone in the nighttime setting and kind of get a feel for how to use them and figure out what the sweet spot for your camera is, and learn how to focus at night as well. And there's a few tricks on the trade of that, where you can maybe put some tape on your camera lens to figure out, you know, if you align your tape to kind of figure out where your ideal settings are. Now, while you're out there, you also want to be avoiding smartwatches or bright phones and tablets. So make those as dim as possible so you can still see them, but not, you know, blow out your night vision. And also, if the screens have the ability to turn on a night light, which kind of puts an orange or yellow or red tint to your screen, that'll be ideal too, because it'll keep your eyes nice and dilated. And that's true about even your headlamps. So if you have a headlamp, you want to use a headlamp that has a red light coloring or a very low light setting, because you want to keep your eyes as dilated as possible to see what you're seeing. Now, some observation notes on where it's best to see it, as well as how to plan for it. So as Lourdes touched upon earlier, it's not a nightly occurrence. So there are some planning that you kind of need to know before you go out. So the first would be the aurora potential. If there's no potential, you get to go to bed on time and not even worry about it. The location is ideal here because not all locations are built the same. The weather is also another thing that you kind of need to know ahead of time, and also moonlight. So for the aurora potential, there are several websites that you can kind of touch on. Some of them are listed here. So spaceweather.gov, solarham.net, Aurora Live. So all of these kind of give you an idea of what might be coming. The two that I frequent the most are spaceweather.gov, because it kind of puts in a numerical forecast, which you can see here in this slide. So you can kind of see the numbers that are listed on the bottom there. Those are the KP numbers that Lourdes was kind of touching upon earlier. So essentially, the larger those numbers are, the better our chances are of seeing them. For our latitude, typically about a 4 is the lowest that we can kind of see them, but you have to have really ideal settings where you're standing to look at them and so on and so forth. But for the most part, most of New England is going to need a 5 or greater to see them. And the larger that number is, the better your chances. And then the next slide shows solar ham. Once you start delving into the aurora potential, you're going to start learning about all the various numbers and speeds and tilt of the aurora. That plays into whether or not we can see them at this latitude. So essentially, if you have a negative BZ, B as in boy, Z as in zebra, if that's a negative number, that means they're going to be tilted a little bit more south and allow us a better opportunity to possibly see them. So the next thing would be also downloading some apps for your Android or iOS device, since most people have at least one of the other. Some of them are listed there. So the Aurora Borealis forecast alerts or My Aurora forecast, but there's a slew of other ones. But I would recommend checking the ratings and reviews of those various apps to see what other users are saying about them. Most of the apps all are pulling in the same data, so you're not going to get one that's going to be superior to the other. It's just how they are relaying that data, or maybe how reliable that data is or how those alerts work, because some work better than others. So just make sure you're reading the ratings. Another place would be also social media. So I would recommend following a lot of space weather or solar physicists, as well as Aurora, Northern Lights, or space weather accounts, or photographers from around the region. Because if they're seeing them, a lot of them will, likely tweet that, or Facebook or whatever, that they're seeing them. So locations are also ideal. So for our location at this latitude, the south side of ponds, lakes, bogs, swamps, anything with a large field of view. So even agricultural fields can be a great location. So by standing on the south side of that, you're basically able to see at a long distance to the north and possibly see some of the auroras that might be occurring, as well as rise of land. So hills, overlooks, or vista points. And as you see there, I say lower mountains. Higher elevations do provide you some views, but there are some downsides to the higher you go. So low is kind of your friend. Now for New England, the other thing that you have to contend with is light pollution. So unfortunately, we don't have a lot of dark skies around New England. The map that you see on the left there, all the colorations that you're seeing are levels of light pollution. So parts of Maine have really great dark skies, especially if you're in the upper parts near Caribou or Presque Isle, or if you're in down east Maine near Bar Harbor and those areas, you're going to have some really dark skies. But around most of New Hampshire, Vermont, New York, you're seeing a little bit of light pollution, not only locally, but also from Canada, as well as light pollution to our south. So there are a lot of places that you're going to have to kind of play along with or go out and experience for yourself to see what the typical light pollution is for that location, because some areas will be really unusable and just drowned out by too much yellow or local light casting. But some areas around here do have some nice dark skies. Even parts of Massachusetts, if you get away from city centers, can have some dark skies for you to view. Now, the other thing to kind of pay attention to, though, is weather. So what will it be when you go out, as well as what will it be later? So is there going to be high humidity, and is there possibly going to be fog expected? Because if you're going to go to the south side of a pond, you're going to be possibly losing your view as that fog builds in. Are there clouds possibly moving into the north that might obscure your vision to the north and see, just cloud bases rather than northern lights? Or you can have, thick low clouds that are going to be blocking everything and not even provide you views overhead. Other things that might be limiting your visibility are rain showers or possible lightning storms, although that can sometimes make for some nice imagery. Haze or smoke that can sometimes lose your visibility out to the horizon, so that can kind of like muddle things a little bit. If it's going to be really windy, that's going to make your camera move, so that's going to make it a little bit difficult. You're still going to be able to see them in person, but photographing them is going to be a lot more challenging. And then how cold will it be? Because you're going to have to prepare to be dressed to stand out there for a really long time, possibly all night without even seeing anything. So you kind of want to know how to wear, what clothes you might need to wear. Now, as I kind of touched upon, higher summits are not always an ideal location. As we touched upon earlier, Mount Washington is in the fog over 60% of the year. So over half of the year, we're going to be in the fog. So that makes it a little bit more difficult to see them because they're not bright enough to shine through fog. So that's just something to kind of bear in mind. Winds also, like I touched upon a bit ago, make it really difficult to keep your camera steady, and aurora predictions are not foolproof. So if you're not a fan of being out in the after hours or sitting there waiting for them to occur, they might not be ideal. And what's also bad is if you hike into a location, you really can't move. So if your location ends up being not a great location, it's not like you can hop in your car and move to where there might be clearer or darker skies. You're kind of, stuck at the location that you chose. So it's just some things to bear in mind. Now, observation modes, as far as the moon goes, it's always important to know where the moon is at as far as opacity, because the brighter the moon is for our location, the lower your chances are of seeing the northern lights from our location. Not impossible, just increasingly improbable. So if you have a full moon, it's going to take a really strong aurora for us to see at this latitude. But you should also know when the moon might rise or set, because you might be able to go out before the moon rises and see it before it's drowned out by the moonlight, or go out a little bit later and see when it might be after the moon sets. And then knowing where the clouds and light and everything else is going to be and interacting with each other, because you might have enough clouds that kind of muddle the moonlight and allow you a darker sky to your north to be able to see what might be occurring. Now, a few additional things to kind of keep in mind is make sure that you're dressing appropriately, because you might be stuck out there for really long times during the overnight hours. Again, preparing for the weather, not only for your clothes, but also, you know, how they might affect your views to the north. Bring somebody or something to pass the time with, because you might be there the entire night and not see a single thing, or you might go out and be lucky and see it as soon as you step out of your car. But it's always good to kind of have something to pass the time with, so that way you're not feeling like you're wasting your time. Also, when you're going out to locations where others might be photographing or observing them, please be respectful of people that are around you, so that way you're not ruining their shots or getting in the way of their shots. I know this kind of sounds weird, but know which way is north. I've gone to parking lots where I've literally pulled in and saw everybody facing south, and I'm like, what are you looking for? And they're like, the Northern Lights. I'm like, it's literally in the start of the name, it's north. So just know which way is north. And then also lower your expectations. So a lot of people, I think, have this idea that they're going to be, you know, really bright and singing a song as they're like sparkling in the night sky. But in reality, they tend to be a little bit dimmer than what you see in photographs. So as you can kind of see a side by side here, the left is more or less what you're going to be seeing on social media or those low light webcams that might be able to pick up all that sensitive light. Whereas the image on your right is going to be more or less what you're going to be seeing. And if you're not even used to the night sky, you might actually just be seeing the light pollution from Canada and assuming that you're seeing light from the Northern Lights. But in reality, it's just light pollution, unfortunately. So it's always good to kind of lower your expectations and know that they're a lot dimmer to the human eye than what your camera might be seeing.
All right, so I'm gonna take it back. Actually, let me go back here for a second. If they are not intense enough, they might look to you like a cloud. So the way you can tell that is something different than a cloud is that you will be able to see stars through it. Clouds will not let stars be seen through. Also, the unnatural movements, you know, or the shapes might help you distinguish it from fog or from light pollution. So we only have a slide or two here to bring us to the end. Ryan mentioned that you need at least a K index. This is the easiest number to find in the forecast. The K index of 4 means that the auroras might happen up here, and it's not over us, but we can see them from the south. The one that happened at the end of March, it was in the high 7s, and we even reached 8 that night. So it was really, really out of the ordinary. And that meant that the auroras were visible from many different places, not just here in New England, but further south. And that was when we were able to take, my student took this picture even from town. And even though there's very clear light pollution around, they were strong enough to be seen and photographed through that. We like the strong events for the auroras, but something we need to keep in mind is that when the auroras are very strong, that means that there is a very strong geomagnetic event happening. And the stronger and the more beautiful the auroras are, the more in trouble we are. Power grids, radio communication, satellite communication, GPS, you know, we might lose electricity. Somewhere I was reading that if the same event as 1859 happened again, it would take us months to recover. And there would be a severe disruption of anything you can think of. And it would cost trillions of dollars. So even though we'd like to see those auroras, hopefully it won't happen in the near future. And hopefully we, you know, get better at building infrastructure that does not get affected so much. But they are connected. The geomagnetic storms and the auroral events is what causes them. So just wrapping up these things that are beautiful and fascinating and, ethereal, hard to describe, happen all the time in the high latitudes, sometimes obscured by clouds, sometimes not. And when they're stronger, we can see them from lower latitudes. And once in a century or so, maybe from the tropics. NOAA has a space weather prediction center that provides the forecast for those KP indexes. And if you want to even have a chance to seeing them, besides having clear weather, you need an unobstructed north view. And you want to prepare and use all the tips that Ryan gave us earlier. So I was going to play this time lapse, but instead I encourage you to go and Google, go into YouTube and search for Mount Washington Aurora time lapse and enjoy it, so that we can actually move on to answer any questions people might have. So let me get off the share and see and give it back to Brian.
All right. Thank you so much, Lourdes. Thank you, Ryan. That was, Lourdes, you mentioned it at the outset. Obviously, you're literally writing a book, a textbook, trying to cover all this information. So really just scratching the surface here, but appreciate everyone sticking with us this evening and for joining the full program, because we had to limit ourselves in terms of what could be covered tonight. But that being said, there's some great questions already in the chat here. If you're joining us on Zoom, remember to use the Q&A button. You can find it at the center of the toolbar at the bottom of the screen there in your Zoom window. And we'll just get right to it. We have a number of great questions. We'll get to as many as we can here. The first one, Ryan, I know just really briefly you'd mentioned it. And for anyone else who doesn't know, Marcia and Quentin had asked the question, just clarifying, hey, what's forensic meteorology?
So that has to do with loss of property or loss of life or related type events where the weather might have been involved. And so the insurance company or provider might hire somebody to look backwards in time to figure out, was it actually weather related? Is it a fluke of nature? Was it, something sporadic or whatnot? And kind of put together a window of what occurred leading up to the event that lost that property or life, and kind of figure out the weather behind the various aspects that are being investigated.
Yeah, fascinating field. And I know there's some people work in that field who end up, time and again being expert witnesses in trials and things like that. So definitely a unique application of atmospheric science. I had a question from Jay, and Lourdes, maybe a good one for you. I know you did mention the Southern Lights, the Aurora Australis. I always mess that one up. But anyways, we're in the Northern Hemisphere. So we're, obviously taking a look at that and have a keen interest in that. Jay was curious, are the Southern Lights rarely mentioned because there are fewer people in the far Southern Hemisphere, or is there any difference maybe in frequency or anything like that to your knowledge?
They are almost mirror images of each other, but the difference is that the latitudes in the Southern Hemisphere where the auroras are most visible, that auroral zone, is not, doesn't pass through any large population centers, only parts of Antarctica that have people living there some of the time. So most of the time they're not visible unless they are extremely strong and, they can be seen in Southern Australia or the southern part of South America.
Yeah, interesting. That's what I might have guessed as well. But then again, it's one of those things: if a tree falls in the forest, but no one's around to hear it. Situation. I don't know. But anyways, we're getting pretty good with sensors these days all over the place. Marcia and Quentin asked another good question, and I'm not sure if you had captured this before, but for Galileo, if he was talking about the Northern Lights, was he seeing them in Italy?
So the latitude of Italy is similar to that one, the place where he was seeing them from, similar to ours, maybe a little further south. So I would say it'd be like seeing them from Pennsylvania. You don't see them too often at all, but when you do see them, they're very impactful. And he definitely would have been seeing them toward the north because he was too far south to see them above. So yeah, I dug out all the details at some point, but I don't have them in front of me.
No, fascinating question, and one that even, when we compare the weather of New Hampshire, it's funny or the climate, I should say, it's funny to look at a map and see latitude wise, we're about the same as the
Yeah.
Mediterranean, yet we don't have a Mediterranean climate here, obviously. Another question from Doug, and I don't know, again, apologies if you did cover it, but Lourdes, is there any seasonality to the strength of auroras? I mean, I know it's, as you're mentioning, certainly solar driven, but
so
what about that?
This is very tricky. Obviously the sun has the sunspot cycle, which is an 11-year cycle. So when that's in the maximum activity, we are more likely to get more solar events that can enhance the aurora. But that's not seasons, that's 11 plus minus year cycle. However, there's a tricky thing, which is the alignment of the magnetosphere with the solar magnetic field. When that solar magnetic field is straight south, it can produce the strongest, for the same solar activity, it can produce the stronger aurora activity. And that alignment north-south of the magnetosphere and the solar magnetic field is easier to get during the equinoxes. So in a little tiny bit, yes, it is easier to get the needed alignment in, late September or in March, but there's no guarantee. And the solar magnetic field can sometimes point south, sometimes north, because you can think of it as a ballerina, you're spinning. Sometimes you see the bottom of the skirt, sometimes you see the top of the skirt. So that there can be a little bit, but the solar activity is way more important.
Yeah, it's a lot of variables coming into play, certainly, and trying to, not only for the event to occur, but then, as Ryan was covering, for you to be able to see it in the first place.
Mm-hmm.
And I should give kudos here to eagle-eyed viewer Karen, who noted, hey, both the Carrington event and the Red Aurora occurred in the month of September. Maybe there's some significance to that. Hey, look at that. Good job, Karen. A really great, fascinating question from, my goodness, from John for Ryan. Hey, Ryan, I mean, put you on the spot here, but is there like a most memorable experience you have photographing the aurora?
Well, one of them would be the background of your you. So that one only lasted a matter of minutes. So I went out to do the hourly weather observations, which we take up on the summit, saw a slight glimmer of green, grabbed my camera, ran out, snapped about 15 minutes worth of photos. It was bright enough, as you can see in the image, to light the undercast as well as the snow, a light green tint where you didn't even need a headlamp to walk around on the summit because it was so bright. I thought, well, I should go wake up my coworkers because they might want to see this. So went inside, woke up everybody, and it was done. And then they were like, sure, it happened. I'm like, no, wait, I've got photos. But yeah, that was definitely a good one. And then there was the other one that Lourdes had in her slide presentations where we were standing on the observation deck, all kind of, hands up in the air. That particular event went from sunset to sunrise. It was an all-nighter. And was strong enough, and our winds were low enough, and it was overhead briefly, and to the point where we could actually periodically hear it. So that was pretty memorable.
Wow, that's yeah, having seen just one on the summit, can't say I had a similar wow experience, which I appreciate, Ryan, the side-by-side imagery about what you might photograph versus what you might see. Certainly there's definitely a difference, and it helps if it's a strong event.
Yeah.
Maybe just, I know we're running a little long, but just one more question perhaps for each of you. There's a great question, and sorry if I'm already losing the person's name who's asking, but it was making me think. So Natalie was asking if Lourdes, if you can talk maybe a little bit more about any current research or big questions into the Aurora, anything NASA or others are currently looking at, the big questions currently being investigated that you're aware of?
So there are a lot of big questions that have to do with the interactions of the two magnetic fields. And there are satellites that are placed in space measuring the strength of the magnetic field and the speed of the solar winds. And a lot of the questions have to do with this snapping together of the two fields, like two bubbles side to side, the magnetic reconnection. We do not fully understand all the mechanics of that. And also for the same solar activity throughout the night, sometimes there's a burst in activity that happens that has to do more with magnetosphere fluctuations. They call those auroral substorms. And that's also a big area of research. So basically you're watching it, it's calm, maybe you're in 70 degrees latitude, it's green glow, and suddenly it goes off for a few minutes or for an hour, and then it's gone. So that's different than the big solar forcings that cause it to be spectacular and somewhere else. So and I've only explored a little bit, so I'm sure there's way more questions out there in areas that I cannot even imagine at the moment. Yeah.
Well, thanks, Lourdes. I know for the most part you're focused. I mean, even your research, maybe not in like full on space weather and all of that, but
I've been reading a lot. It's like I had to learn a whole new discipline in order to understand enough to be able to explain them. I'm focused on the optical part of it, right? What we can see in the sky, but to do that justice, I need to learn a little deeper.
Well, don't sell yourself short. That whole space weather department at Plymouth State University may be starting soon.
I know.
All this. Well, and so, hey, Ryan, a couple. Now it has to be two questions for you because so many people said, "Wait a minute, you can hear the aurora. What does that sound like?"
I don't know how to relate it. It kind of had an electro sound to it, like I forget what those like 80s and 70s events were, where you put your hand nearer to the pole and it made that woo sound. But it kind of had like an electrical EDM kind of sound to it. It was really weird and hard to explain. But maybe Lourdes, do you know of any better explanation?
So I haven't looked into it too deeply, but I know auroras emit a lot of radio frequencies that can be very disruptive, but those you can detect more with instruments, or maybe you're trying to listen to AM, FM radio. It will cause interference just like lightning does. But I have heard about these sounds coming. If you think about it, sound is a vibration that makes your eardrum vibrate, right? So these really energetic electrons are coming into the atmosphere, and they can cause waves that I imagine can be some of what we hear as sound. But I haven't looked into it too deeply. That would be awesome.
That's the whole acoustic aspect of this that we didn't even think to talk about this evening. That's amazing. Well, and so Brian, lastly, I don't, I hesitate asking the question. I don't know if you're willing to give away the real secrets here, but I mean, are there any sites for viewing aurora specifically, or maybe general regions that you might recommend, say just for northern New Hampshire, perhaps for those folks with us that might be looking to travel around?
Yeah, for northern New Hampshire, a really popular location, although bear in mind that if it's a well forecasted event, you might be sharing it with a whole lot of people. Is Chocorua Bridge. So on the south side of Chocorua Lake, there's a little bridge that goes across that everybody loves to photograph from, but at nighttime it can provide some really spectacular views, as well as a really unique mountain perspective or profile that a lot of people like to go and look at. But that's far from the only one. Any lake, like I said. So if you look on a map, just look for an area that might have a boat launch or a public park that might be on the south side of a pond or a lake. But just make sure if you are going to go to those locations that you can visit them after hours, as you don't want to be trespassing, especially like a lot of wildlife refuges, words. Those can have some stipulations on, can't visit after an hour after sunset to an hour before sunrise. So you don't want to be disruptive there, or some areas might have a private boat launch and you don't want to be trespassing on any of those. So just wherever you do choose to go and look at them, make sure that you're allowed to go there. And then also another good location would be the vista points on the Kank, if you're around the Conway area. Those provide some nice elevated views to provide you views to the north, or from the Conway area going over to Freiburg, where there's a lot of agricultural fields that you can kind of stand near or by, and that'll provide you nice views up into Evans Notch and areas further north.
Well, those are some wonderful suggestions. Thanks for not giving away your specific spots to everyone, because as much as I'm sure we'd all like to roll up right next to Ryan Knapp so you can have a personal Aurora photographer helper, hopefully you can keep your spots relatively quiet for now and keep enjoying those. But Ryan, Lourdes, thank you both so much for preparing this presentation. I mean, I know this is stuff that's right up your alley anyways, but still really appreciate both of you sharing your expertise tonight. And for all of you joining the program this evening, if you enjoyed tonight's program, certainly we'd encourage you to make a donation to support programs like these and keep them free over at mountwashington.org. You can hit the donate button in the upper right-hand corner. And if you have any thoughts about tonight's program, or if you have a suggestion for future programs, please take some time to fill out the Google Forms survey that'll show up in your Zoom window or in the follow-up email that comes tomorrow after joining the Zoom program. And then finally, don't forget to join us for another really exciting Science in the Mountains program next month, Tuesday, May 23rd. We're looking forward to hosting Dr. Ralph Keeling from the Scripps Institution of Oceanography at UC San Diego, who will be discussing trends in atmospheric carbon dioxide, all about the history of the Keeling curve as well. So don't forget to register for that program. You can watch any previous programs you may have missed as well over at mountainwashington.org/SITM. Well, thanks again, Lourdes. Thanks, Ryan. Really appreciate it. Thanks all of you for joining, and we'll see you again soon. Have a great night.
Thank you. Good night.
Right.